Okay, good morning, everybody. I'm trying to present my screen. Hold on, please.
All right.
Please, can you see my screen now?
Yes, we can.
Okay, thank you. So, good morning, everybody. My name is Precious Raman, and I'll be presenting the topic evolutionary algorithms. So, when I got this topic, I was very confused. I didn't know what to do because I had no idea what evolutionary algorithms are. So I had to go online, I had to search, I had to understand the concept, and I was able to discover one or two things, and I would like to share these things with us today. So I'll be taking my outline from introduction to conclusion. We cannot talk about evolutionary algorithm without talking about evolution. Evolution is the whole base of the process. Evolution is a biological process that involves the change in the characteristic of a species over several generations. So it is like the change in variation, the change in trait, the change in feature of a species, whether dog, man, goats, and other species over several generations. So diagram of the evolution of ape to man. So we are all familiar of the concept of evolution of man, how man evolves from ape, and then we can see that evolution played a large and integral part of this process. You can see how the ape was evolving from stage one, stage two, stage three, stage four, up to intelligent human. It relies largely on the principles of natural selection. The natural selection was a notion postulated by Charles Darwin, where he was talking majorly about the survival of the fittest. He was talking about how species have several, they have different individual of species usually have different individual of different variation. So it is whenever this variation is subjected to environmental change, the the organism, the individuals that are able to that are able to adapt and survive are called the strong organisms, and then they are the ones that would not die off, unlike the ones that are very weak and would die off. So, example, I'll be giving us an example: the adaptation of black peppered moth over the white moth in the Industrial Revolution period. In the 1700s, the white moth had a higher population than the black peppered moth, and that was because moths had mastered the ability to camouflage on they can camouflage on a white tree. So because of that, the black peppered moth had a lower population. And during the industrial revolution, there was like a generation of suits, and suit was everywhere. Suit was on the trees, suit was on the houses, and then the black moths were able to camouflage. Because of this, population decline. We can see from generation one, where we had a large number of white moths, generation two where the black moths, generation three where the black moths, even till today the black moths are actually more than the white moths. So I'll be introducing evolutionary algorithm. Evolutionary algorithm is a population-based meta-heuristic optimization algorithm. So population-based because we cannot one evolutionary algorithm is not based on only one agent, only one individual. It's like the combination of several individuals. That is why it's called a population based, and it's materialistic because it's like a higher level procedure designed to find, generate, or even select the best procedure that may provide the best solution to an optimization process. So evolutionary algorithm is a procedure that selects a best procedure, the best solution to a problem. And then we all know what optimization is. Optimization means getting the most out of something. So it is like a nature-based approach to optimization. It is based on nature. It got its inspiration from nature. So getting the most out of something and making it better. That is the same thing with evolution, because evolution gets the most out of a particular population, makes it better, move on to the next population, move on to the next generation, makes it better, move on to the next generation, and if that and that until it gets the best generation like we humans. Evolutionary algorithms is inspired by the notion of survival of the fittest by Darwinian theory of evolution and Mendel's genetics. I talked about the survival of the fittest from the Darwinian theory of evolution, whereby Charles Darwin talked about how the individuals that are able to survive they have traits and variations that they've acquired over the years. And Mendel's genetics has to do with an offspring having the same gene as the parent. So evolutionary algorithms are based on these two theories. It imitates some aspects of natural evolution. It imitates reproduction, it imitates combination, mutation, and even selection. We'll be seeing this as we are going on in this life. So moving on, we talk about the idea. Evolutionary algorithm is based on the idea that adaptation is intelligent. So it is not possible for a dull organism to adapt. It is not possible. So it is only intelligent organisms that can adapt, an intelligent organism that can adapt to a particular environmental change. So it's also like the general notion is also based on the fact that if evolution can produce amazing beings as humans over many generations, then we should be able to use the same process artificially to produce optimal solutions to the problems in the society. So with this notion, some scientists came together and felt that this would be a perfect theory to incorporate into solving problems in our society. I'll be talking about the history of evolutionary algorithm. The idea of applying Darwinian principles to automated problem solving dates back to 1940s, even before the advent of computers. So a lot of people came together. They were thinking that, okay, this is something that could work. And in 1948, Turing proposed genetic or evolutionary search. And by 1962, Raman had executed experiments on optimization through recombination and evolution. So it was able to understand the concept of evolutionary algorithm, and that was in 1962. And after this, there were a lot of implementation based on this idea, and about three were developed in the 1960s. We have the evolutionary program that was developed by Fogel Wash. We had the genetic algorithm by Holland. We had the evolutionary strategy by Richenberg. We had Richenberg and Schwerfield. Yes, over the years, and over the years, a lot of other areas were also explored under the umbrella of evolutionary algorithm, and some of them were developed. Some algorithms were developed. We had the differential algorithm. We have the genetic programming, and others. Moving on, I'll be talking about the general scheme of evolutionary algorithm. But this diagram, I might not explain this diagram because if I start to explain it, we might not really understand. So I will go towards the theory, and then from the theory we'll come back to the genetic scheme, to the general scheme. So there are five major stages of evolutionary algorithm. We have the initialization, we have evaluation, we have termination, we have selection, and we have generation. The initialization stage is like the generation of the population. It is where you generate a population of individuals. So it's like some kind of big bang. I know we are familiar with big bang. Some kind of big bang where the initial population is just generated out of nowhere. So a population is a group of possible solutions to a problem. If you have a problem, if we want to apply the concept of evolutionary algorithm, we would like try to generate possible solutions that can solve the problems. And the population should be homogeneous. The population should all be focused on a particular problem. You cannot have a population that is focused on another problem, another problem. It will not be homogeneous. In fact, it can cause a whole lot of problems. So how do we initialize or even generate our population? We can generate our population randomly. We cannot overemphasize the technique of randomness. We can generate our population randomly. We can generate it by embedding domain knowledge, the knowledge on that solution. If you have a particular knowledge of the solution, you can use it to generate or seed the population. So there are two different ways to generate our population. We can generate this randomly, or we can imbibe domain knowledge to seed the population. So moving on to our evaluation stage. The evaluation stage involves the definition and implementation of fitness function. If we are very familiar with deep learning in AI, we know there are a lot of functions. We have linear regression, we have sigmoid. Yes. So the difference between this function and this particular fitness function that we're talking about, those functions, sigmoid and the others, are like defined. They are already defined. So in fitness function, there's no particular definition. There's no one way to it. So fitness function is always fine-tuned based on the solution. So it's only when you have the solution you can pick a particular fitness function. And the higher the fitness function, the better the population. So the higher the fitness function, I would explain all this, the better the solution. I'll explain all this later. Every solution is tested against the fitness value. Once we have a constant fitness value, our fitness function, if we say our fitness function is 150, we evaluate every of our solutions that we initialize. We test it against the fitness value, and then we give it a fitness score. So the fitness functions are usually randomly defined. Sometimes, if we do not have a prior knowledge of the solution, it is important that the fitness functions are random. Also, the best solution, the best way of getting our fitness function is based on, having a prior knowledge of it. If we have a prior knowledge of the solution, we can, be able to define our fitness function, and then we'll not have to go to and fro. So moving on to the termination stage. The termination stage is actually to prevent the loop from running forever, and it involves determining the loop termination point. Without the termination point, the loop will just keep running. So the termination point is usually decided before the entire process, and there are different determinants. So it could be based on the maximum number of generation. You could say that, okay, this generation, I want the number of generations that my loop will go over. I want it to be like 50 generations. I want it to loop over 100 generations. I want to loop over 10 generations. And at the end of that 10 or 100 or whatever it is you have chosen, the loop will end. It could be based on the minimum level of biodiversity. So if your biodiversity is reduced to an extent, you can tell the code that once you see that the biodiversity has reduced in my generation, end. You could tell the code to end whenever it gets to a particular fitness that you've chosen. You could say that, okay, if my fitness function is 150, when you notice a fitness score of 200, and it could be based on certain number of generations when no significant fitness change occurs. So when it gets to a particular generation and it notices that there is no more fitness, the fitness scores are just the same, they are constant, we could tell the code to terminate. So moving on, we'll talk about selection. The selection is the stage of the fittest. So selection is just main survival of the fittest. It is when you select it is when you select the parents from the individual, from the population, and we do this using a variety of techniques. So the number of parents selected is decided by the engineer in charge. So you could decide that, okay, in a pool of four population, or in a pool of four individuals in the population, I want there to be 3 parents. So it is up to the engineer to decide. Yes. And then there are different selection procedures. There are 2 different types of selection procedures, and these selection procedures are based on like conditions. So number one, if your fitness values are different, for example, if you have a fitness value of -10 and you have another fitness value of 100, another one of 1000, you should do rank selection. That is when you rank all the solutions based on their fitness value. Like you rank via as descend order. Yes, the higher, you remember I was talking about the fact that the higher the fitness function, the better the score, the better the solution. So another selection procedure is the roulette wheel selection, and this one is based on probability, and it is used whenever the fitness values are not very different. If you have like 10, 11, 12, 13 years, we use the roulette wheel selection. You can see the diagram here where we have the selection point, and then each fitness value take a share of the roulette wheel. We have the fittest individual has the largest share of the roulette wheel, and while the weakest one has the smallest share of the roulette wheel. Then we'll rotate the wheel, and then whatever share lands on this selection point will be a part of the parent. Moving on to the variation stage, the selected parents are used to produce the new offspring population in variation. So these selected parents, we now use them to produce the new offspring population, and this is done via 2 procedures, 2 techniques. We have the chromosome crossover and we have the mutation. Chromosome crossover is also known as recombination. So I'm very sure I told us earlier, yes, that it uses the the procedure of natural selection. So recombination is part of natural selection, mutation is part of natural selection. So recombination is like a combination of different traits from parents to form new offspring. Via our diagram, you can see that a part of a parent combined with another part of the parent to form an offspring. So that is how it is. They keep crossing over, they keep combining to each other in order to form new offspring. However, it is very important that we combine. Combination is like the most important part of variation. It is the most important part of variation. And the combination should not be 0%. That means you're copying the parents. The combination also should not be 100%. It shouldn't be 100% that you are copying everything. No, because sometimes some offspring used to have the same gene as the parents. So the combination can be between 80 to 90% or more or less, based on, it's actually based on the AI engineer in charge. Moving on to mutation. Mutation is the introduction of new feature to an offspring to create a whole new individual. For example, in these children, yes, looking at this diagram again, I can decide to take a part of the offspring A, the first bar. I can decide to change a part of that offspring A to yellow. Yes, that is mutation, because you are introducing a whole new feature into the children. And then this mutation occurs rarely. It shouldn't just occur anyhow. Even in humans, our mutation does not occur anyhow. It doesn't occur. It comes once in like 500 years, 5 million years. That's how it should be. And mutation should not be 0%, because that means that there's no diversity. You know, you keep crossing the same feature, the same thing every time, and then it gets boring at some point. Then mutation should not be too much too. Huge variation prevents convergence and it leads to competition, because the species will not even be the same thing at the end of the day. By the time you are imbibing mutation at every point in time, before you know it, all your population is no more homogeneous. So we'll go back to the diagram of the general scheme of, yes. So looking at this diagram, you can see initialization. It's initialization of the population. There should be a pathway showing evaluation between initialization and parent selection. But then I guess the diagram does not have it. But after population, we can see the arrow is moving towards the parent. It's after population, you do your evaluation. After evaluation, you select your parents. You select the parents. After selecting the parents, you do your recombination and mutation. After doing your recombination and mutation, you get your offspring. You evaluate your offspring's fitness to know the kind of fitness your offspring have. Sorry, hold on. To evaluate the kind of fitness your offspring have. Then your offspring, if they've not met your condition, will become the new population. So that is how it works. Moving on, we'll be talking about, I have the pseudocode for a typical evolutionary algorithm here. It begins with the initialization of the population, evaluate each population. We have the loop, select the parents, to combine the pairs of the parents, mutate the resulting offspring, evaluate the new candidate, then select individuals for the next generation. I have a case study here in order for us to better understand it. We have 4 individuals. We have man A, man B, and man C, and man D. Yeah. I made a mistake there. In a hurdle race, fitness function of jumping the hurdle is 150. To jump a hurdle is 150. And I've already given the fitness score for each of the individuals. Man A had 90, and that's because of he's disabled and he has a big head. Man B has 200, and that's because of his long legs and slim body. So it's easier for him to jump the hurdle. Man C has short legs and plump body, so he cannot jump the hurdle, but he was able to get close enough, or he was able to try to jump the hurdle, so I gave it 120. Man D has very short leg and a long upper torso. It's more like a middle man. Those people that battle with dwarfism, middle people, little people, very short legs and long upper torso. So I gave him 100. So from this, once we've gotten our fitness function, we've already done our evaluation. Yes. So we'll move on to selection of the parent. And I want to select only 2 parents here. I'll be selecting via the rank selection. So I'll be selecting man B and man C. Yes, and man C. And after that, I'll be crossing, I'll be doing variation on man B and man C. And that means I'll be crossing long legs and plump body. I'll be crossing short legs and slim body. So my man E, which is the offspring, we have long legs and plump body. And my man F, yes, we have short legs and slim body. So these are my offspring. And if I say that, okay, what I have right now is not, once I do my fitness evaluation of the offspring and I see that, okay, what I have right now is that, okay, what this person has right now is not the end result, I cannot terminate. So man D and man E will become the next population. I hope we are following.
Yes.
Yes, thank you. So we'll be moving on to the classes of evolutionary algorithm. We have 5 classes. We have the genetic algorithm, we have differential algorithm, we have evolution strategies, we have evolutionary programming, and then we have genetics programming. Number one, the genetic algorithm. All of these 5 actually work with using, all of them work using this particular pseudocode. All of them, they basically make use of this pseudocode, but there are like one or two little, there are little changes. Yes, because that's what differentiates them. We have the genetic algorithm. It's actually the most widely known evolution algorithm, and it was conceived by Holland. That's the USA. It's a USA citizen. It has a binary representation. Whenever we see genetic algorithm, we see zeros and ones. Illustration later. We have fitness proportional selection. So the fitness selection is actually it makes use of the roulette wheel. It gives everybody the opportunity, the chance to be selected. It makes use of low probability of mutation, which is good. And emphasis on genetic inspired recombination. I talked about recombination earlier. It uses the general principle of selection. You select the parent, you cross them, recombination, and then you mutate, which is like the general principle. So we can see here an illustration of genetic algorithm. The initial chromosomes are the parents. We have 2 parents here. We see after the crossover, we see that they crossed about the first 5 and the last 5, the first 5 and the last 5 of the 2 parents. We can see it here. And then mutation, they converted some ones into zeros. So this is how genetic algorithm works, and this is how it looks. It's filled with zeros and ones. We have the differential algorithm, which is the second one. This algorithm is very similar to genetic algorithm. However, the difference there is that it starts with mutation instead of selection. It starts with mutation, crossover, and then selection. So you mutate first, then you recombine, and then you select. Moving on to the third type of class of evolutionary algorithm, we have the evolution strategy that was invented by Richenberg and Schwerfield. The offsprings are generated by recreation of a new individual from the parents using Gaussian distribution. So instead of using the recombination, instead of using the normal recombination method, the offspring will first create, like, the parents will first new individual will first be created from the parents using a distribution, and then this new individual or temporary individual that has been created will be crossed and then mutated to produce new offspring. Then the fourth type class of evolutionary algorithm, we have the evolutionary programming. This algorithm is very similar to the evolutionary strategy. The parent population is mutated to produce new individuals. So the parent population is mutated immediately. They are selected, they are mutated, and there is no form of recombination. So they mutate them and then they produce new individual, bam, just like that. Then we have the genetic programming. Unlike genetic algorithm, this algorithm is represented by programs. So unlike the zeros and one, we know that genetic algorithm is represented by the binary, so zeros and one. But this one is represented by program. This particular class of evolutionary algorithm is basically, it's more like a program creating a program. So it's like a program that creates another program. It's a tree-based algorithm instead of binary. So it's a technique used in evolving computer programs that solve problems. So instead of a software engineer having to write a code, keep writing a code, you could imbibe programming, and then the genetic programming technique would keep evolving the computer programs, keep evolving the computer programs until it becomes very smart in solving problems. So we are moving on to the application of evolutionary algorithm. Evolutionary algorithm is applied in various ways, in various aspects of life. In fact, all I have here is not even enough. So number one, we know the normal optimization, getting the best solution out of a pool of solutions. It is used to design. It is used to design. You can design neural network, electronic cycles, or even structural design. Then we have planning, used for planning in routing and scheduling, can be used for routing and scheduling. Identification can predict future values from medical data. It can identify that okay, once this happens, this is going to happen. Once this happens, this is going to happen. In the form of game playing, can be used to create lots of games, DNA analysis, diagnosis of heart disease, and detecting spam messages. We have the shortcomings of evolutionary algorithm. There is no how we would have before we talk about the shortcomings of evolutionary algorithm, I want to talk about why people employ evolutionary algorithm. This is number one. I'm sorry, I apologize. This is not in my slide. I just realized it now and I'm going to make adjustments. Number one, it is easy to code. It is very, very easy to code compared to the ones you have to write a lot. You have to write lots of code. It is easy to code, and it provides many solutions. So you have a lot of solutions. You can pick any one of your solutions. Although at the end of the day, it is streamlined to the best one. But if you don't want the best one, you can still pick any other one. It can be parallelized, as in it can be broken down and sent to different machines. So because of the fact that they can be slow, I will talk about that later. Because of the fact that they can be slow, they can be broken down into various parts, and these parts can be sent into different machines, so they can be executed differently. Now we have the shortcomings of evolutionary algorithm. They are very slow. They are very slow because of the fact that they make use of the concept of evolution. Evolution takes millions of years, thousands of decades. So this, they don't take millions of years like evolution, but they are very slow compared to other techniques like deep learning. Deep learning is fast, but you cannot. It is not all the solution, all the problems you solve using deep learning that you can solve. It's not all the problem that can be solved. I don't know how I'm going to put that, but it's not all the problems. Yeah, you cannot only use deep learning to solve majority of the problems in the world. You can also make use of evolutionary algorithm. They can be very slow, they can be very sluggish. That is why it is very important that your population is not too much. If you have a lot of individuals, if you have many individuals within your population, it is going to be very sluggish. But it's also important that your individuals should not be too scanty because you will not get enough solutions. So your population should be in between. Fitness functions may not be easily defined, like I said earlier. It's not like sigmoid or linear regression. So it's just like you only defined you only the AI engineer handling the evolutionary algorithm only defines based on the solution or based on his knowledge of the solution. So it's not something that you just know that okay, fitness function for this particular problem 200. No, it doesn't work that way. So in conclusion, the evolutionary algorithms are popular research domains and they are usually applied in solving many industrial problems. Every year, many new modifications, like I said earlier, they keep developing every year, every day, are proposed, and it is widely believed that new militaristic evolutionary algorithms will emerge in the future. Thank you for listening.
Wow. Thank you very much, Precious. That was a good one.
Thank you, sir.
Um, where do I start? You did justice to your topic. Really, this is something I've been looking forward to. You have demonstrated clear understanding of your topic. That's awesome. So um you have given me a chance now to ask more technical questions. Much of my questions in previous sessions have been just fundamental. So now going a little into some technicalities because you have shown very strong understanding of your topic. So
Yes, sir.
before I proceed, let me take questions from the house. So if you guys have questions, please go ahead and shoot your questions.
Mine isn't a question. I just want to tell her that her presentation was awesome. Hey, Precious, you
Thank
did well.
you. Thank you so much.
Yes, anyone else? Okay, so let me know which time. I would start with your slides. I'll start with your slides. So before I go into other things, um, I think generally your slides have been okay, the structure and everything. Although there's still some areas I would want you to improve on, especially with text. Go to the next slide. Let me show you something.
Okay.
So in the outline here, I think
Okay.
maybe the spacing between the bullets you could reduce.
Okay, sir.
You're gonna have space, a little space between conclusion and this green, the bottom shape of the this green shape at the bottom. So let there be some space, just like you have some space between introduction and the line above it, this red line. We also need some space between conclusion and the green box, so
Okay.
that the whole thing doesn't really look so lumped up. Then let's go to your next slide. I noticed you used you you used justify in your um, in your
Yes.
paragraphs. So for that, there's a kind of there are unnecessary spaces between the words. Okay, and it might not really look so for something like this. I think it's better you just use the left align. Okay, so just use left so that you don't have unnecessary spaces between words. Because as long as a particular word cannot fall into a particular line, the words remaining on that line will just show so much separation. That might not really look so nice.
Okay, sir.
Okay, so but other than that, I think you know what? Just let me let me see if I can point out another thing. Why the spacing here
Yes, I wanted
between the first
to.
bullet point?
I wanted to like. I wanted to make it obvious that the first one is like definition, while the last two are like the
Uh-huh. Okay, in that case, a trick you can use here. Can you come out of this presentation to your main PowerPoint screen?
Okay.
Okay. So what you should do, um, open the text box. Just enter the text box, yes. Then take away the bullet points from evolutionary algorithm.
Okay.
Just backspace from there, yeah. Then after algorithm, put a colon.
After algorithm.
Yeah.
Oh, yes, sir.
You can put algorithm in uppercase, the A in capital. Then take away this is here so that you have evolutionary algorithm, a population-based meta-heuristic optimization algorithm. Very good. And you can then take up that space between that sentence and the second bullet point. Can you hear me? Okay.
Yes, I've done that.
So meta-heuristic, you can change the font color. Go to the font color. You can put that in any color of your choice. Normally, I prefer. There are some colors I prefer, but I can't see them here. But you can just choose any other color of your choice, just to highlight the difference between you know those ones and the main header. You get.
Yes, sir.
So your choice of color should be something. It should be sharp. It should be. It should not be so light. It should be something that we can easily notice when we look at your slide. So I think this is okay. So let's proceed. So you can come back to slideshow. So these spacings, just work on the spacings.
Okay, sir.
Yeah. Sure, let's continue. Um, I would. I'm done with your slide. Let's not waste so much time there. Okay, so let's start
Okay, sir.
from the beginning. Okay, where you introduced evolutionary algorithms. I really have to say, I'm just trying to be careful not to overpraise you, so that you will not miss out on the corrections. But you really did justice to this topic. I'm so happy to start the session like this. So even if along the way it's like the whole thing is just dragging, I know that you had a good start. Okay, so you talked about what an evolutionary algorithm is, and the moment I saw the topic, I mean definition, population-based meta-heuristic optimization algorithm, I was already taking notes. I was going to ask you what meta-heuristic means and what optimization means, so that we are sure that we are not confusing ourselves with buzzwords and definitions. But clearly, you already gave that the definition of those. This is just what I want to see. Okay, when you throw certain buzzwords in a definition, don't assume you understand it. Break down the words. Even a word as similarly simple as optimization, and break it down. Let us understand what this really means. All right, so let's move on um to others.
No, it was
Did you
my
say
sister.
anything?
Apologies.
Okay, okay. So we already talked about. I mean, you already talked about how evolutionary algorithms are inspired from the whole theory of evolution. So this is just an aside. Okay, it is just an aside. Do you believe the theory of evolution?
I don't believe so. I don't believe
Okay,
it.
so um, science is known for. When I mean science, I'm talking about natural sciences, physics, chemistry, biology. They are known for this this very strong strong reliance on experimental validation for anything. So when physicists proposed Big Bang theory, okay, the physics community, even though a lot of people, you know, looked at the theory and feel we can work with this, okay, this looks robust. Yet no one can say, no physicist can say it out with confidence that Big Bang theory, is the theory of the beginning of the universe. You know why? Because for you to make that claim, you have to prove it. And the only way you can prove it, this is not mathematics where you prove with theorems. The only way you can prove this is by giving us experimental validation. So how can you validate something that happened according to you billions of years ago, unless you want to travel back in time to see how it happened? Okay, so we are looking for other ways to validate that theory using certain, pieces of uh, um, pieces of study from current events in the galaxies and in the universe at large, so that if we can connect the dots between how galaxies evolve and all of that, we can use that to deduce that okay, this is what happened at the Big Bang. Until then, no physicist can say that the Big Bang is how the universe came about. Even though some physicists, they don't claim, they say this is a possibility and they hold it strongly, but they can't claim. That's how much physicists would respect, experimental validation. You understand? So outside physics, a lot of people think that we believe the Big Bang Theory, or that there are some physicists that believe the Big Bang Theory. Yes, there are some physicists that want the Big Bang Theory to be true because they find it more convenient than the idea of God. So they want it to be true, but they know that except they want to ruin their reputation, they cannot make huge claims. They just hypothesize, and they hypothesize strongly, to really carry people along that theory. So coming to biology too, it's still pretty much the same thing. Before you make a claim, you have to validate experimentally. So you have your hypothesis, but you are going to design an experiment, run an experiment, then evaluate the entire thing. And if your experiment supports the observed, whatever you've observed, then you can make your conclusions. The same thing with chemistry. But it turns out that for the first time, evolution theory came up, and we have a lot of people swaying for it and completely swallowing it without, having any experimental evidence to support that. And according to them, I mean, there are a lot of things that we can use as experimental evidence, or that we need as experimental evidence to propose, to support evolution. So many things. Okay, but those who, you know, support evolution are looking at some of the some really weak evidences like fossils. Okay, fossils from extinct organisms, and according to them, that's how that is why they believe that evolution is true. But those evidences are really, if you ask me, those evidences are weak supporters of the theory. So for me, I don't believe the theory. But coming to AI, the theory has been developed. Even if it is blindly developed, you can still pick out relevant knowledge from it and use that now to get some things done. And so when we are using evolutionary algorithms in AI, I think I find it more convenient that we can apply some of the strategies now when building machines. Okay, so when we're talking about real life, someone cannot just propose a certain theory about how life came about and expect us to swallow it. But when we're dealing with machines, we can pick up the ideas and apply them to machines. So that's how I view the whole thing. All right. So much said about that. Um, let me talk about. Let me ask you about. Um, let's go to your next slides. I've noted some things, but I want to get to where you are. Next. Yeah, move on again. Let's. Okay, so let's look at this. The general scheme of algorithm. Now, I like how you put this in diagram. And when I was looking at this, I was looking at some things in genetic algorithm. So I was going to give a topic on genetic algorithms, but I just thought, okay, genetic algorithms are part of a component of evolutionary algorithms. So let me see how you guys will handle evolutionary algorithms, and let's see if someone will talk, a little bit about genetic algorithms, so that I don't have to give that separately. And you really did well on that. I have to comment that. So I have done more commendations than criticism so far. Hopefully, I get to a point where I would give some criticisms. So let me see your next slide. Yes, very good. So I'll be talking about this. So you talked about 5 stages of evolutionary algorithms, and interestingly, the steps you've highlighted here are steps we can really specify for genetic algorithms. Okay, so in your genetic algorithms, did you give the steps for working or implementing a genetic algorithm?
Yes, I,
Because
I, I did not really give the steps, but I said that this is like the
okay,
general scheme, this is like the general overview of all kind of algorithm. It starts with
yes,
initialization, then there are like little changes
yes,
depending on the
exactly,
kind of algorithm we're working with.
exactly. So there are some other algorithms that will have all the algorithms more or less follow these 5 stages. Okay, but the genetic algorithm kind of directly copies this. Okay, so your other algorithms may have slight variations. So I want you to tell me. Let's start from initialization. I would talk more when we get to selection, but let me start with initialization. So how do you? Okay, you already have them here. Um, yes, let me use this now. When you're initializing initializing a population, okay, um, where do you really start from?
Where do we really start from? For my own basic
Yes,
understanding, I think that it is just something that is random, but then you look at the solution. It is very important you look at the problem rather. It's very important to look at the problem and then think about possible solutions, random solutions that could be, you know.
okay, so you're randomly initializing a population. That's very good. And
Yes,
when you
if we do
randomly
not have
initialize,
yes, I
yes,
said if we do not have a prior knowledge of the solution, of what the solution could look like, we could just
okay,
randomly initialize the solution
okay,
or
that's a good
population.
one. Now, uh, um, how do you when you're dealing with a population now, much of what we're talking about is borrowed from biology, okay, from the biological notion of evolution. So when you're initializing a population, what are the things in the population you're considering? Okay, that is, how do you create representations for the population?
Creating representation for the population.
Yes, that is the random population you're trying to initialize to work with.
Yes, sir.
Okay, how do I put this question? You're dealing with a population. In biology, you're talking about maybe individuals, for example. Okay, but in those individuals, what are the things you're really looking at studying? Okay, that is, what kind of representations are you creating? Do you
Okay.
understand? That is, given this individual, okay,
The,
these are the things that we are going to use to represent the individual. That's what I want you to
yes,
tell me.
we look at
Okay,
the
very good.
features, and then they should vary in each individual. Although there should be no great variation, the variation should be such that the individuals are still homogeneous.
Okay, okay, that's a good one. So I just wanted to hear that. Now, uh, coming out of biology a little, okay, if you're dealing with AI systems, because I think one of the limitations of your presentation today, I would say, is the fact that it didn't really specifically go into applications in AI. So I would have loved to see more of evolutionary algorithms at work on AI systems. So if we're talking about AI systems now, what are the things you'll be looking at for your population? When you're talking about population, we'll be talking about population of agents or of models. So either you're dealing with agents or models. So your agents could be intelligent agents, um, and they could be any of these general machine learning models.
Yes, sir.
Okay, and of course, there could also be other types of there could be other types of AI models, like problem-solving models or heuristic search models. Now, given you're dealing with models, now you're talking about a relation of models. What do you think? I don't expect you to have the answers actually, but I just want to see how you reason about it. So, what do you think would be the representations you're dealing with here? For humans, the representations you're dealing with, you are representing individuals as genotypes. You are representing them as chromosomes that consist of a set of genes. You know, but coming to AI systems, how do you? What representations are you going to be utilizing?
Okay. There was something I read online when I was researching this topic. There was this game. There's this game. Yes, I've forgotten the name of the game, but there's this game that was initialized
Okay.
using evolutionary algorithm, and this game, it's like a person jumping from one bar to the other,
Yeah.
like all these normal games you have, but this game is intelligent. So they were talking about how, when you get to the difficult levels, there are some difficult levels that might not be easy for people to just, for people to scale. So there's a way they used to calculate every jump. Like before you get to a particular level, there's a particular jump that will take you to the next bar. You have to get that precise jump. So they'll calculate the height, the distance, and all from my own understanding. So for that jump, the features that will be calculated will be the height, the distance, and some other mathematical functions.
Okay. You've tried in that response. So just on a more precise level, okay, if you're dealing with AI systems, agents or models, what is really a model? Okay, so you have a classifier, a model that carries out discriminations between your class labels. Now, in a classifier or your classifier, what really is your classifier? That is, if I ask you, show me the classifier, what does it look like?
Classifier,
Yeah, a classifier model.
a classifier model. Well,
Yes,
I'm sorry,
what does it look like?
I think I have to read more about that.
Okay, okay. Okay, a regression model, for example. Okay, what would your regression model look like? What really is a model? Okay, I'm not talking about the meaning of a model. Okay, I'm talking about what is your model? Is it an object? Is it a software? What exactly is it?
A model is an architecture.
Uh, Not really. If you say model is an architecture, and that's the problem because in some of our previous sessions, I was emphasizing on the difference between algorithms and models, and I think those that attended really understood that. But now, yeah, that you brought in architecture, and that's more of like that's a more deep learning term because in classical machine learning we hardly talk about architectures except in a few cases, but in deep learning it becomes compulsory for you to talk about architectures. So we cannot talk about algorithms versus models versus architectures. So an architecture is not really a model. An architecture is like the structure, it's like the structure of the model. So it's not really the model itself. It's like, okay, how do we connect the dots from inputs to outputs? All the steps for. So more or less like the structure of your algorithm, not even really the structure of your model. Okay, so that's your architecture.
Yes, sir.
But now, what I really wanted to point out here is that a model is an equation. Okay, so what are we really building when we build a model? It's just we're trying to figure out the parameters of the equation. Okay, what are the optimal parameters of the equation? You know what the parameters are? If you have an equation like maybe y equals to m1 x1 plus M2x2 plus M3x3 plus beta. That is a model, which means it's a function that your algorithm has learned from the data.
Yes.
Now, that model, the dependent variable is y, the independent variable is x, but we have other things that we can see in the model. They are called parameters. So your M1 is a parameter, your M2 is a parameter, your beta is a parameter. Parameters are numbers that we want to estimate by running an algorithm. Okay, so at the end of the algorithm process, we should be able to give optimal values for M1, M2, and beta. So that is why the process of obtaining these values is usually called optimization, and we use so many optimization techniques.
Yes, I wanted.
Why? Because
Okay, hold on, sir. Please.
yeah, continue.
Yes, the M1, M2, and beta, are they like constant, or they're like a
No,
value
they're not.
you just generate?
They are not constants per se. Okay, just to make sure that I'm not just talking things you cannot see. Let me just use a slide to illustrate. So I would override your screen, but afterwards you'll be able to you will be able to still continue. So don't worry about stopping your screen.
Okay, sir.
Yeah, I'll just override it here. So I used the illustration yesterday. So let me just show you. This is taking time. Okay. So I just did a small illustration here. So you have this this equation here. I hope you can see my screen.
Yes, sir.
Okay. So you have this equation here. This is the equation of a straight line. And this is the equation of a simple linear regression model. Okay, so this is these are the variables y and x. Then this is your parameter m. This is your parameter beta. Okay, basically in linear regression or in a linear model, this beta parameter is like your intercept on the y-axis. Okay, so in more sophisticated models like a polynomial regression model, you would have more parameters for your m, which of course when you're computing, you put all those parameters in a matrix, and then you would do some matrix transformations, maybe to do dot product instead of a cross product. And so at the beginning of your model building, you would have determined that this is the equation this is the model I want to build, which means the equation for this model looks like this. If you want to build a simple linear regression model, you already know that this is what the equation will look like. Okay, and so you want to build a linear regression model, but you need to the linear regression model must have fixed values for m and beta. Okay, for a polynomial regression model, if you identify that, okay, I want to use a quadratic function, then the highest power will be 2. So you identify that this is what you want to use. At the start of the algorithm, this is what the model looks like. But at the end of the algorithm, your model ends up looking like this. Okay, it must have values for M1, M2. So the goal of your regression algorithm is to learn the parameters of that model. So given the data, it optimizes or it produces the optimal values for your parameters. So they're not really constants, they are parameters. The statistical term for this is parameters. It's like saying these are quantities that are going to determine the fit of the function, what the fit will look like. Okay, what the fit of the line will look like. So normally in an optimization process, we initialize when we initialize start with arbitrary values of m and beta. The algorithm just gives arbitrary values for m and beta, and then checks the fit on the data. Okay, if the line doesn't really fit well, it then begins to run the optimization processes such as gradient descent, and as it runs those optimization processes, it continues to optimize the values of m, whether m1, m2, and even beta. It continues to optimize those values until it gets to an optimal value of each of those parameters where the line best fits the data. So the learning process or the learning algorithm is not just trying to learn a model, but the more specific thing it's actually doing is to learn the values of the parameters of the model. More precisely, to learn the optimal values. Optimal meaning there can be so many possible values, and the line will have so many different types of fits for each of these values. But there's going to be just, a specifically small set of values where the line would have a really suitable fit. So the most accurate line of fit will be those that have the most optimal values for the parameters. Does that make sense?
Yes, sir.
Okay, so back to your presentation. Let's spin your screen. I don't know if our screen is pinned from your own views. Otherwise, you can pin it. All right, so what led me to that illustration? I was trying to talk about where were we? Yes. So your model is an equation, okay, and all these models, whether it is machine learning models or intelligent agents, they are really just equations. So when we are trying to create representations for these equations or for these models, when it comes to the work on evolutionary algorithms, then we are not just, we're not just in a biological, from the biological view or perspective, you want to represent the individuals as genotypes, is it not? But in the AI view now, you want to take those functions or those models. You know what the equation looks like, so you want to optimize the equations. You understand?
Yes, sir.
Now, a set of all those models make up the population that you're interested in. For example, if you're dealing with classifiers, okay, let's say you have you want to run a classification process. Okay, and maybe you want to, instead of using a single classifier, you want to have a classifier system, which is a set of classifiers, and then you want to optimize this entire system. So which means you're not just dealing with a maybe a logistic regression model. Okay, you are dealing with so many logistic regression models that fall into a space, a particular space, which means they have they have they have they fall within an interval of a particular space. Okay. Now, to represent these models or the individuals in this classifier system, to carry out representations for them in order to build evolutionary algorithms, okay, we are going to represent that entire set, okay, as a set of phenotypes. But the phenotypes we're dealing with here, okay, uh, um, that is that is the classifier system is a set. Each individual model in that set is a phenotype. from, of course, from the biological notion of phenotypes. But now there's going to be a slight difference. Okay, we are going to encode each phenotype as a binary code. I don't know if that makes sense.
Yes, sir.
Yes. So you know what binary codes mean, which means zeros and ones. So we'll represent each of the models. Now that we're coming to a computer science perspective, because it doesn't make sense if you're talking about, yes, these are genotypes. These are genotypes. What's a genotype as far as a computer system is concerned? It doesn't make sense to use genotypes. So we have to use computer language, because we're going to translate all the algorithms from the biological notion of evolution. We're going to translate them to computer executable programs. I don't know if I'm making sense here.
Yeah.
Okay. So we encode or we represent these individual models as binary codes, so that each model is either 0 or 1. Type. I mean, the entire genotype. A phenotype is an individual model. Am I correct? A phenotype is an individual model in the system. Okay.
Yes.
Those of you that are biologists
Yes.
here, correct me if I'm misusing the terms. Okay. Then a genotype is the entire set of all the phenotypes. Am I using the notion properly? Who are the biology people in the house now? Raman, you're not talking. Yeah,
Yeah,
biologist too.
the phenotype is like the set of genotypes.
Okay, the phenotype is a set of genotypes.
Yes.
Uh, okay. Not a genotype being a set of phenotypes. Hello, can you hear me? Any
I
other
can hear you.
person? Can any other person put us on track so that I'm not misusing the terms? Yes, Samuel, go ahead.
So I'm not saying to answer question. No. Yeah,
Okay,
I don't know shit in biology. I'm just saying that.
okay, because sometimes the terms, I myself, I confuse the terms, but I know that you have individuals either being phenotypes or genotypes, and then you have the entire set as now Raman has further confused me, so I'm waiting for her to respond.
I'm here.
So did you catch what I was trying to say?
My Wi-Fi went off.
Hello.
My Wi-Fi went off, sir. Can you hear me?
Okay, yes, I can hear you now.
Yes, sir.
So I'm trying to ask, which is the genotype and which is the phenotype? Is the phenotype a single member of the system, and the genotype is the entire set of all those members? Or which one is the set and which one is the individual member?
The genotype usually creates the phenotype. So
Okay, so
yes,
genotypes make up phenotypes, right?
yes.
Okay. In that case, your genotype, I think, is just misuse of your confusion with the terms on my own part. So in that case, your genotype will be each individual members in that set. Okay, they are represented as binary codes, zeros and ones. Okay, then your phenotype will then be the combination of all that genotype,
Yes, you're
which
very right,
is
sir.
okay. So which is now going to be a larger binary number. I'm just holding a second. Let me power on my gen because this guy is just too polite. Okay, guys. So I'm back. Now, as I was saying, where did I stop? What are we talking about? So I guess I was talking about your. Okay, yeah, we're trying to create representations for AI systems. Okay, and I talked about um, how you carry out the representations for an AI system. So the first thing when you're building an evolutionary algorithm in AI is you want to design a representation, is it not?
Okay.
So that's the first step. You are going to design a representation. And so to do that, you need to encode this in computer language. Okay, so each individual system, I mean, each individual model or agent in that system that is in that population will be encoded as I mean, will be given a binary code. The entire population will not be a larger binary number. So it is this with this representation now, you can then begin to run your evolutionary algorithms. Of course, following some of the steps that you already highlighted. All right. So moving on. Let me go to your. Where did we stop on your slide?
Up here.
Okay. Now another question. I've already told you about. Um, I've already talked about how you encode the binary system. I mean the system, the population of AI agents that we want to use to run the evolutionary algorithm. So when we have such a system, okay, when we have such a system, what is the goal of the evolutionary algorithm? What now becomes the goal of the evolutionary algorithm? You know what I'm trying to do here is trying to help you connect the dots to the application in AI. You
Okay.
get, because
Okay.
when you talked about evolutionary algorithms, you talked about it from a more general level. You understand? So we have to now bring it home to AI systems to to help us understand how we can achieve this in AI. Of course, it's not something that's the entire process cannot be exhausted in a session like this. But I just want I want you to just kind of reason about it. Like I said earlier, I don't expect you to have all the answers. Okay, but I want to just look at your. I want to observe your thinking process and see how you uh, can come up with with how you can come up with ideas, or how you can come up with answers to questions you've never really considered. So back to what I was saying, you have that system now of AI models or agents that have been encoded as binary numbers. So how do you what is the goal of evolutionary algorithm now for such a system?
Okay. So the goal is to get the best model, the model that will perform the best among all the models that we've pulled together.
Okay, are you trying to get the best model or the most optimal model in that set,
The most
or are you
optimal.
trying to optimize? Just hold on, because if you look at what's I think Victoria took that topic on swarm intelligence. It was like you guys are talking about almost the same thing. You're dealing with population. She dealt with population. She dealt with individuals in the population. She dealt with members of the population trying to arrive at the same goal. Okay, but in our own case, the optimization is like global optimization, where she's interested in optimizing the entire system, optimizing the goal and the movement of the entire system, the the evolution of the trajectory of the entire system. That was more or less the goal. Okay, but in your case, the goal is like I want to really understand the goal here. Or I want to see if you understand the goal. So, what is the goal in your own case?
The goal is to optimize, like, you said it already, but I forgot how you put it.
No, don't say it how I put it. Say it in your own way. I'm more interested. You can tell
It's
me what
like
you
to
said
optimize
initially.
a set of, not the entire model per se, not the entire model per se, like a part of the model. in a way. I don't know how I'm going to explain it.
Okay, so don't say
Hello, sir.
hello.
Yes, sir.
Can you hear me now?
Yes.
Okay, so don't say model. Okay, we're
Okay.
talking about an entire system of models.
Okay.
So it's not just a model we are working with when we're working with the population. So what would your goal be working with that population
Our goal is to get the optimal model, the model that
in
will
that system?
yes, that will perform the best.
Okay, so this is like a model selection procedure, right?
Yes. Yeah.
Okay, thank you very much. Now, in order to arrive at the best performing model, are you interested in a single best performing model? Are you interested in a number of optimal models where others will be dropped?
It's going to depend on the person. It's going to depend on the person in charge of the model. Depends on what the person wants. If the person wants more than one model that can, that can carry out that wants more than one model within the pool of those models, or the person wants
Okay,
just one model, or if the person wants a generation of models.
okay, I think I like that, a generation of models. So which means you're going to be having parent models. So you decide how to select individual models to become parent models. Is it
Yes, yes, sir. Yes,
okay?
sir.
When you're trying to, can you hear me? I think my network is bad. So what are you really doing here? What are you really doing to when you're trying to arrive at best performing models or optimal models? What are you? What is the keyword from evolutionary algorithms that you're actually doing to the other models?
You're evaluating the models.
No, evaluating is like more of computer science, machine learning terminology. But from evolutionary terminology, what are you doing to those other models that are not going to are not going to emerge as the best performing models?
They're not going to emerge as, but you are terminating them.
How do you decide how to terminate them or when to terminate them?
I think it depends on the fitness score. You see if your model.
Thank you. Oh, thank you. So you have a fitness function, right?
Yes.
And it is based on that fitness function that you are getting, values. And so by those values, you select the individuals, that is the individual models that should be replaced. Is it
Yes.
not?
Yes, sir.
Okay, so that's it. You've done a good job. I like your responses. Okay, let's proceed to the next question. I think I actually have more questions for you than I've had for others. So let's look at your. We've talked about initialization, right?
Yes,
And
sir.
I think that's where we stopped. I mean, that's the last slide we looked at. So let's go to okay, yeah, evaluation. Let me see. Um, where does selection come in this whole process?
Selection comes after this process.
That's after evaluation.
Yes, sir.
Okay. Um, I don't think I really have a question here. We already identified that you are using a fitness function to evaluate.
Yes, sir.
So it is it is with the fitness function now, the values you get from that tells you which ones need to be.
Eliminated.
Where does selection come in? I'm seeing termination here.
Selection comes. This termination is like a loop.
A loop
It's like a loop. Yes,
within where?
within the code. Like immediately after evaluation, you will- let me show you.
Okay.
Okay, this diagram. You have
There's a loop in
initialization
step.
in step. Let me show you.
Okay.
Excuse me, sir. Let me show you the pseudocode.
Okay, you know what? Go back to okay, yeah, show me the pseudocode.
Okay, so this is the
I
pseudocode.
really wanted that pseudocode. Very good. I was so happy when I saw the pseudocode because I'd already pointed out. Why not show me the algorithm for the steps in the pseudocode? Okay, go ahead.
So we initialize the population with the random candidate solution, like the
Okay.
models. Then evaluate each model, then repeats until termination condition, like when you're going to, if not, the loop will run forever. It will keep checking, making the offspring the new population, keep selecting, recombining, mutating, and then it will keep doing that unless a termination code is satisfied, condition is satisfied.
Okay. Okay.
And
So that makes sense. Uh,
yes, and I talked about the determinant of termination.
and what is that?
The maximum number of generations, like epoch.
Okay.
Then the minimum level of biodiversity, like at a point maybe you can tell the code that okay, when the biodiversity is low, like it's very low.
In AI
Which is
terminology now, what would that be? Okay. In
I'm
AI
trying to
terminology,
relate it,
what is the maximum number of generations? What is generations you're dealing with?
like the models, the
In the
models.
models now, you're dealing with what exactly? What is the exact for the generations in the model architecture? What are you really considering here?
We're considering the I don't have an idea.
Okay, let me not spend so much time on it. Let's talk about um, we'll go back to that algorithm again. I want to ask a question from there. So your selection process comes within this stored loop,
Yes, sir.
and of course, it's like repetitive selection, or should I say recursive selection, where you start with selection, you end with selection, you loop again until the termination condition is satisfied, right?
Yes, sir.
Okay, so I want you to talk more about selection. Do you have did you have a slide for that on
Yes,
selection?
I do.
Yeah, I want to ask a question on that. Okay, so you talked about various types of selections. You talked about rank selection. How many types of selection did you talk about?
I talked about
Because they're actually
two,
more. Okay, what are the three?
two
You have rank
rank
selection. What are the other
selection
two?
and the roulette wheel selection.
Okay, so at what points, when do you have, or when should you use any of these selection procedures? Okay, when do you consider suitable to use rank selection and to use the roulette wheel selection?
Okay, it's yeah. I said when fitness values are different, like when the fitness values, the rates of fitness or the level of fitness for each model,
Okay,
when these levels are very different from each other, we consider rank selection. However, when these fitness values are not so different, then work with probability. That's the roulette wheel selection.
okay, that kind of makes sense. But we still actually have other selection procedures.
Yes,
Okay, we have tournament selection, and it is a limitation of rank selection that would allow you to use tournament selection. Okay, um, I prepared well for this topic when I gave you guys swarm intelligence, evolutionary algorithms, and what was the other one?
knowledge
Knowledge
representation.
representation. Yeah, because I knew these were more technical topics than the others. And so anyone who presents well, I'm going to ask you, some really technical questions. But the goal is not like you know, to put you off guard, but to kind of guide you into some of the more interesting notions. So I'm talking about a limitation of rank selection. Okay, so if you have a very large population size, let's say thousands of models that you want to work with, okay, that you want to optimize, that's a population that you want to optimize, but this population has so many, it has a very large size, then rank selection would not really be suitable. Do you know why?
Right, sir.
Because the rank selection process is very difficult to implement. Yeah, I can hear you now. Yes, so I was saying that the rank selection would have a limitation because uh, um, you need like for rank selection you need like global knowledge of this set. When I mean global knowledge, you need to have from a glance, okay, immediate immediate understanding of the representation and the model architecture and the inner workings of the models at a glance. This is unrealistic to achieve when you have a very large population size. You get.
Yes,
So
sir.
when you are dealing with a little number of models, it's easy to carry out computations to have a global um, view of the models. But when you now have a large population size, computing, running the computational processes to retrieve knowledge of each of the models in that sample becomes, it becomes computationally intensive and unrealistic. So in this particular case now, we use tournament selection. Okay, and there are so many versions of tournament selection, but the goal here is like you are trying to you just randomly select, from the term tournament. Okay, tournament selection. So it's like a competition is going to take place here. Okay, so we'll bring in some notions from competitive AI. So it's like a competition is going to take place here, and in this competition, you are now going to randomly select, from that population, the best among them in terms of the fitness value, just like we talked about, and then you keep that in a separate set. So you continue to repetitively carry out on the remainder of the population. You repetitively carry out, these steps, the tournament selection procedure randomly, and then from that random sample, you select the best, you keep them, you append to that set like that. When you're done with that population, you now come to this set that has been newly generated, and you repetitively carry out that process. You see that by doing that, you are kind of terminating the weaker models. I don't know if this makes sense.
Yes, sir, I understand.
Yeah. So all this termination process and the entire process in that loop of trying to terminate, you know, uh, um, models or agents of lower fitness values. You know, you are now doing this recursively, like tournaments, instead of considering the entire set and trying to know each of the fitness values for the sets by running fitness functions on each of them and then ranking them. It will not really be optimal to do that when the models are so large,
Yes,
when the number of models are so large.
yes,
Yeah, so tournament selection is also a very good way. I hope you guys can see that AI is really very interesting. There's a lot of interesting AI outside machine learning and um, outside your conventional machine learning and deep learning. And all this we are working with, we are still using all these algorithms to work with models, And in the industry, evolutionary algorithms are very useful. So this is not that like an abstract area that is not utilized in AI. When companies that deal with a lot of models, that use thousands of models or build thousands of models, they run all these evolutionary algorithms for optimization, because the conventional optimization algorithms from machine learning would no longer be would not be efficient at running model selection at scale. You need selection algorithms that are so robust, selection algorithms that carry out recursive termination of weak models. So that's why exposing you to some of these topics helps you see the much of AI outside the conventional machine learning and deep learning.
yes,
Okay, so I think I've talked about tournament selection, so you can just look at that. That's like a third component or a third type of your selection process. There are still others. I can't seem to remember which exact ones at this time. So let's just work with the 3. Okay, so that's a good one, Precious. Now,
Interesting.
I want to talk about crossover. Okay, where does crossover fall in here?
Variation.
Do you know what? You know that's this what's it called? The algorithm you showed me, um,
The pseudo
even
code.
though that's a pseudocode, yes, you showed me. It's in fact this is genetic algorithm pseudocode. This is genetic algorithm, and normally in your evolutionary algorithm, the first step in evolutionary algorithm, what's the first step in evolutionary algorithm? In running an evolutionary algorithm?
Initialization.
No, I told you the first step.
Representation.
Yes, you first of all design a representation of the system. That is, given this population of models or agents you want to work with, I'm going to now, instead of the biological notion of encoding each individuals as genotypes and then the set of individuals as phenotypes. I hope I'm not using the biology. I hope I'm not misusing the biological terms here.
Mm.
Genotypes are the individuals, right?
Yes, sir.
And the system is the phenotype. Okay.
Yes.
So coming to AI now, each individuals in that system will be encoded as binary numbers, and then the entire binary system is what you want to implement your evolutionary algorithm on, and then select the optimal models from that scenario. So your typical EA actually begins from representation, but when we now narrow it down to genetic algorithms, okay, the algorithm for that starts with initializing the population with random candidates solutions. So you're generating a random population of n models or n agents. Now, the next step here, you're evaluating each candidate. Okay, using what are you using to evaluate the candidates?
Sir?
I said in the next step now, you're
Yes,
evaluating
sir.
the candidates. And what
Yes,
are you
sir.
using for the evaluation?
Fitness function.
Very good. I'm really checking how well you have mastered this topic. And so far, um, you you have shown you have shown solid grasp of the topic. It's not like you just came to present and to read out something, but you really understand what you're talking about, which I really like that. So, you're not just talking based on your slides, and then when I ask you a question, you've forgotten what you talked about. So thank you very much. Fitness function. Now that we have a fitness function, we run that fitness function on each candidate. And what are we getting when we run the fitness function?
When we run the fitness function, we get our fitness score.
Yes, you get your fitness value. And then with that fitness value, you proceed to with those fitness values, you proceed to the next step, which is the termination loop. Okay. Now, in that termination loop, here I did not really see this is your genetic algorithm, but okay, we have selection here. Where does crossover come in this
It's
loop? Can you hear me? Hello.
Mr. Zion.
Yes, can you hear me?
Okay, sir, I can hear you now.
Okay, so I was saying, where does crossover come in this loop?
Crossover is the same as the combination.
That is after selection, right?
Yes.
Okay, very good. Okay. Let's go to your crossover slide. So just like we did for representation, where we translated the notion from biology to I want to now do this with your crossover. Okay, so this variation is part of the the termination loop, right?
No, it's the variation encompasses the crossover and mutation.
Okay. And wait, go to the previous slide. You know what? I'm getting really confused because of the way you use bullet points. So let's do some adjustments on your slide. Okay, let's start from the first step in this EA scheme. Okay, so the first step here, take away the bullet point from initialization. Let that be a subheading. Yes. So you can put that, you might want to use numbers, or you can use I instead of 1. Just use I.
Yes, sir. I.
Use capital Roman numeral. Why I'm saying you should use capital is because later on we're still going to have no, put a dot, not a bracket. So later on we're still going to have what's it called? We're going to have 1, 2 coming under. So I think the next steps. So let's go to, you can remove that space, remove a space between that and the initialization. So your slide structure is very important. It has to be well understood by your audience. Let's move to the next slide. Evaluation, put that as number 2. No, here.
Yeah.
Then, yes. Then the next slide. Put that as number 3. So where did variation come in? Just wait. Hold on a second. Go back to the first termination slide. Okay. The last 2 bullet points here, just so that we're not confused, cut them out
Okay.
and put them on the next slide. I think what you have on the next slide is like a continuation of these bullet points here, right?
Yes, sir.
Okay, so put that before this last bullet point. Okay, then termination, of course, still put your number 3 there for termination, so that it looks exactly like the previous slide. So that's very important, so that when we are looking at a slide, especially technical people like myself, when we're looking at a slide, we are really wondering what is the drama happening here. We want to understand what you're doing. So I've really enjoyed this topic. Precious, thank you very much for your presentation. I really have to commend you.
Thank you, sir.
Yeah,
Follow your footsteps, sir.
We thank God. So what am I trying to say? I want to see where the termination. Hold on, this is becoming the algorithm is initialized, right?
Yes,
And
sir.
after initialize, you have evaluate. Have you done evaluate? I think evaluation was your number 2.
Yes.
And then what was the number 3?
Number 3 is terminate.
Terminate.
Yes, sir.
So should this really be number 4? This should be like number 1 on that is Latin numeral number 1
Okay, sir.
under Roman numeral 3. I don't know if that makes sense.
Yes.
That is, you have selection, crossover. When I say recombine, sometimes I'm mixing it, like I'm confusing it, because we use crossover more in the AI side. You guys from biology use recombine, but we understand it better as crossover. But you've mentioned you use the 2 together. in the previous one of the previous slides. So let's go back to your selection after termination. So I really want to go into what's it called? What's it called? I want to go um, into crossover, but I just want to be sure that you have everything right here. Let me see the previous slide. Termination. And so I think the next slide, we should just use selection. I mean, we should use 1 to represent selection.
Okay, that means there are no because at the beginning I said there are like 5 stages of evolutionary
Let me
algorithm.
see those stages again, so that it will follow the breakdown you have given earlier. We don't violate that breakdown.
Yes, sir.
Oh, in that case, no problem. Use number 4 for selection, and for variation, use number 5.
Hello, sir.
Yeah. Are you
Okay,
in the 5th one?
I'm on selection.
Okay. So let me just ask this question on crossover. Give me a brief description of crossover again. Okay, crossover is your
So
recombination step, right?
yes, it's a combination
Okay,
step and
so
it's a combination of different
uh,
traits from parents to form new
sorry,
offspring.
where did this variation come in again? After what step?
It comes
That's this is the
after,
5th step
yes, this is the 5th step. It
after
comes after
selection.
selection, after selecting the parent.
Put that as number 5.
Okay, sir.
That's variation, Roman numeral 5, so that I don't get confused, because when I'm seeing that bullet points, I'm confused about the order. So in AI, we use what we call variation operators, okay, for these crossover steps, or just like you have said here, the recombination steps. So we use variation operators. Okay, so they're like mathematical operators that perform the recombination. Now, when we come to crossover, okay, when we come to crossover, how do you, just like we did for representations, how do you relate the notion of crossover now to AI? First of all, tell me what crossover really is. What are we dealing with here when we're talking about crossover? And let's now see how we can translate the notion to AI.
Okay, the combination of different traits from parents, like from the model, parent
Okay.
model. You remove some traits from the parent model and then combine
Okay.
it with another trait from another different trait from another parent to form new offspring. And then this is done like it's done randomly. Yes, it's done randomly.
And what is the reason why we are doing this?
In order for the offspring to have various traits, to have different traits, and the
So that
more.
at the end of the day,
Hello, sir.
can you hear me?
Yes, I can hear you now.
You are checking, you are trying to, more or less what you're doing here is to reinforce each of the individuals with additional traits. So with a random combination of traits, you are trying to reinforce each of the individuals. Is it not?
Yes, sir.
Okay. So the reason you're doing that, what is the end goal of doing this?
So the model can have enough traits.
So that after the models have enough traits, what now happens?
In order for it to be able to have AI fitness score.
You know, our goal here is elimination. The overall here is elimination. The overall here is elimination. So the overall goal is elimination, right? That is, you want to select the best performing models and eliminate the rest. True or false?
True.
So when you're doing all these recombination steps, trying to reinforce each model, it's not necessarily because you want to improve their performance or you want their performance to improve, but because you want to see which ones, after all these reinforcements, which ones still end up not being suitable for the journey ahead. You do understand?
Yes, sir.
So after reinforcing these models, there will still be some more models that will not get the job done. So let's just eliminate those ones. Do you understand?
Yes, sir.
That's the idea here. So now coming to AI, okay, we want to now carry out this, crossover step dealing with agents now. So we're not recombining or trying to recombine, traits. So what do you think will be, what do you think will be randomly recombining here? Like, what do you think will be picking out to add to the various agents in that system?
We'll be recombining the parameters.
Parameters?
No.
Are you sure it's parameters? Remember what the parameters are?
The Y and
Parameters
X.
in the model. No,
The
the
Y
Y
and
and
X.
X. The Y and X are not the parameters.
Yes, the parameters are like the M1, M2, and the beta.
Yes, yes.
Yes, sir. So I'm thinking would, because the parameters kind of define a model.
Okay.
So we're combining the parameters.
Okay, I think we can work with that. We can actually work with that. So let's maybe come to a more specific AI system, which is a classifier system. Have you heard of a classifier system?
Kind of, not very well.
Okay. So basically, your classifier system is like, in AI we talk about expert systems. Okay. But a classifier system now is like it's a set, a set of various models. It doesn't necessarily have to be classifier models. Okay, but this set now will be like we have a set of rules in this system of models, and those rules tell the entire system, how to behave in a particular circumstance. For example, when I mean behave, I'm talking about how to perform or how to act or how to respond. That is, given maybe new inputs of data, it tells the system out the predictions. So an action could be a prediction step, a behavior could be a prediction step. So a classifier system that consists of several agents or models and then consists of a set of rules that tells the system how to behave or how to carry out inference of various actions. That kind of system is called a classifier system. You know why? Because it has to, given a particular action to be taken, a particular decision to be taken, it has to discriminate between the various rules. That is, discriminate to select a particular rule to adopt to respond to that problem or to carry out that inference. You get.
Yes.
So now, when we have such a system, how do we what would crossover be in a system like this? Do you get? So your crossover now will be, we have a set of rules. So of course, each model or agent in that system would kind of follow. They will not really follow the exact same rules since you have so many rules. So let's say for a particular problem, one of the models is selected to solve that problem. Okay, it's going to follow a particular kind of rule, or it has a subset of rules that it would likely follow. So we are not only going to reinforce the each of the individual models, with maybe parameter values. I don't really think that's even the approach used for crossover
Yes,
here.
sir. But can we? Is that a way we can be recombining the rules?
Hello. Yes, it's rules now.
Yes, sir.
Hello.
Yes, sir. I can hear you.
Nothing. Can you hear me now?
Yes, I can. I can hear you.
So yeah, it is the rules now. We are combining necessarily parameters. My network's really
It's better now.
and trying to. Is it better now?
Yes, sir.
How about the sound?
The sound is better.
Okay, so I just wanted to walk you through one of the types of and um, one of the types of systems that we might consider in this case. That's why I brought about classifier system, just to present the notion of a set of rules so that you know that what we are going to be recombining is not necessarily parameters, but we'll be recombining rules and all that.
Yes, sir.
You get? Does that make sense?
Yes, sir.
Okay, we've spent so much time on your presentation again. I mean, on your presentation alone. So I think I will just really stop here. Let me stop here for in your own case. Um, let's I will just leave with these other questions. So you've done a good job, Precious. Thank you very much.
Thank you, sir.
I really have to commend you. You've done so well.
Thank you for the platform.
Okay. And I just hope you've also learned a thing or two from the discussion.
Yes, sir. I learned a lot.
Yeah, because part of what I really want to achieve is to initiate discussions that help you walk through different processes to really understand what is going on, with those processes, so that you are not just giving us what you have and then we say you did well, you did not do well. We also want to be able to help you, understand some more intricate details about what you're doing. Yeah. All right. Thank you very much, Precious. Let's now move on to Samuel. I just hope this one will not take another 2 hours. Of course, by 2 o'clock, I will just really stop so that we'll take a break and then we'll come back by 3 p.m. to continue. Mr. Festus, are you presenting today?
So give me a second to set up.